All right, so through seismograms, two main types of seismic waves can be recognized, and those are going to be body waves, which travel through the Earth's interior, and surface waves, which travel in the rock layers just below the Earth's surface. Within the seismogram itself, the body waves will appear smaller in amplitude, and they will also appear before the surface waves. So this is the seismogram. We're seeing them much smaller, both of these, which are both types of body waves, much smaller in amplitude, and they appear before the surface waves. So we'll go through each of these types of waves in the next couple of slides. So body waves, which will again travel through the Earth's interior, are divided into two main types, and they're characteristic by their travel through different materials, different media. And those waves are called primary waves, or P waves, and secondary waves, or S waves. So primary waves, or P waves, are also referred to as push-pull waves. Sometimes. It's not very common, but that has to do with the motion that they have. So temporarily, they will push or compress the rocks or the liquid or the gas through which they're traveling, and they will stretch or pull those same materials as they're traveling. So this is similar to when you are stuffing your sleeping bag into a bag, for example, and if you don't push it inside the bag, it will kind of spring back. So it will have that push and pull kind of motion. And this motion is exemplified by the slinky in the figure above. So you have compression of certain areas, then you have expansion of those areas, and further compression of the next area over expansion of that area, further compression of the next area, and so on and so forth. So P waves travel through solid, they travel through liquid, and they travel through gaseous parts of the Earth's interior. And they can travel through all of these media because all of those can get compressed and they can rebound after the compression happens, so they can stretch back out. P waves will travel the fastest out of all of the waves, all of the seismic waves. And so they will be the first ones seen within a seismogram. They will be the first ones recorded. Secondary waves, or S waves as they're also called, on the other hand, will shake rather than push and pull. And this motion of shaking is depicted by the rope that is being shaken in the image on the slide right here. So you see the shaking ongoing in this area, and then you have basically no shaking anymore. The next area will experience some shaking, then it will not, and then the next area will experience the shaking. So the S waves do not temporarily change the volume of the Earth's interior as the P waves do. S waves simply change the shape of the material through which they travel. So, because liquids and gases do not resist stresses that cause change in shape, meaning that they won't return to their original shape once the stresses are removed, then the liquids and gases do not transmit S waves. So S waves will only travel through solids. So these S waves tend to travel slower than P waves, given their nature of motion and their nature in terms of what media they travel through. So they will arrive after P waves within the seismogram recording. All right, so surface waves, by contrast from body waves, will only travel through the rocks at a short depth within the Earth's interior. So these surface waves are also subdivided into two types. One of them being the Rayleigh waves, which causes an up and down kind of motion, an ocean wave-like kind of motion. And the second type being Love waves, causing a side-to-side kind of motion. And this is particularly bad for foundations of structures. So surface waves travel much slower than body waves. So in a seismogram record, they will appear the last. And also they will be the largest in amplitude that are recorded within the seismogram as they are at the surface. So that means that where the seismograph is, which is at the surface, it will experience the most shaking due to the surface waves. So this means that they will cause typically also the greatest property damage. So the speed at which each of the seismic waves happens is the following. So P waves or primary waves will typically travel 70% faster than S waves or secondary waves in any solid. And then S waves or secondary waves are about 10% faster than surface waves. Okay, so P waves are the first ones to arrive, then S waves, then surface waves. Okay, so in this subsection, we're going to cover how it is that we locate the source of an earthquake. So when seismologists, which are scientists that study seismic waves, analyze an earthquake records, they first determine the epicenter of the earthquake. One method used to do this lies in the fact that P waves and S waves will travel at different speeds, so P waves traveling faster than S waves. A good example to kind of visualize this is the following. So if let's say that you take up running, for example, when you first start running, you're pretty rusty, and so you're going to run something like 10-minute miles. So you're running 3 miles usually, so you're running about 30 minutes because you're running a 10-minute mile. As you get a little better through time, you may be able to run a 7-minute mile, but your distance remains the same. So you're still running the 3-mile loop that, let's say, is your neighborhood, but now you're saving 9 whole minutes because you're running those 3 miles in 21 minutes because you're doing a 7-minute mile. So if you imagine that now you started running 6 miles instead of 3, let's say that the old you, the rusty you, would run those 6 miles in 1 hour, right? Because you're running a 10-minute mile, 6 miles, you got 1 hour that takes you to run those 6 miles. But the new and more athletic you is going to run those 6 miles in about 42 minutes because now you can run a 7-minute mile. So within those 6 miles that you're running, you're cutting your time about 18 minutes from when you first took up running to now that you're more athletic. So given that example of different distances that you ran and different times at which you ran them, the greater the length that you ran, the greater the difference of arrival from your still rusty kind of you to your more in shape kind of you. Okay? Does that make sense? Think about it again. Pause it and rewind if you need to. But the same thing kind of happens with P waves and S waves. P waves travel 70% faster than S waves. So for every 10 miles, if you would, that the S waves travel, the P waves are traveling 17. So, as an example, this is 10 miles, this is 17. So every kind of second or minute, let's say that it takes an S wave to cover those 10 miles, in that minute, the P wave is covering 17 miles. So, therefore, the longer the interval between the arrival of the first P wave and the arrival of the first S wave, then the greater the distance to the epicenter from that seismograph. Okay? So let me say that again. So the greater or the longer the interval in between the arrival of the first P wave and the arrival of the first S wave, the greater the distance to the epicenter from that seismograph. So if only then is when the P wave arrives to the seismogram, the distance between these two is not very high, so the S wave will arrive relatively soon after. If this is now the time at which P arrives to the, or let's do this one. if this is now the time at which P arrives to the seismograph, this difference in arrival time is much greater than it used to be over here. So, again, the longer the interval between the arrival of the first B wave and the arrival of the first S wave, then the greater the distance to the epicenter from the seismograph. Okay. So, an example of this is shown in the figure to the left that you're seeing right here. So this example shows 3 different seismographs recording the same earthquake event. So we see that the difference in arrival time between the P and S waves is greatest in the seismogram from Nome, Alaska. It's going to be a little bit smaller difference in time in the seismogram from New York, and it's going to be the shortest in time at the Mexico City seismogram. So the earthquake must have been closest to Mexico City, then to New York, and then to Nome, Alaska. A system to locate earthquakes was developed from these observations by using the seismograms from earthquakes whose epicenters could be easily pinpointed based on some other physical evidence. So from these seismograms of those earthquakes, the travel time graphs that were constructed, so travel time graphs like this one over here, and we will be doing this in lab, for example, later on, then it's easier to pinpoint how far the earthquake happened from the observation location. So if we use the seismogram examples on the figure on the left and the travel time graph on the right, which again can look either like this one, but it can look a little bit different like we will do in lab. And I'll show you that the difference in P and S waves can be graphed as one single line. But anyways, using both of those things, so using the specific seismogram records and the travel time graph, we can locate the exact distance from the seismograms at which the epicenter happened. So, if we take New York City's seismogram, for example, where the interval between the P and the S wave arrival time is about 5 minutes, we can see that the epicenter, so this is the interval between the P and the S waves, about 5-minute interval. We can see that the epicenter of that earthquake that it measured falls about 3,700 kilometers from New York, based on this time travel graph. So doing the same thing for Alaska, where the difference in arrival time of the waves is about 6.25 minutes or so, then the distance is about 4,400 kilometers or so from the earthquake. So Nome, Alaska is about 4,400 kilometers or so from the earthquake. And lastly, if we did the same thing with the Mexico City seismogram, we see that the difference in between the arrival of the P wave and the S wave is about 4 minutes or so, which signifies that the epicenter lies about 2,900 kilometers from Mexico City. So a difference in interval between P and S wave of about 4 minutes lies about here, which if we look in the x-axis will be 2,900 kilometers from the observation point.